Greetings and welcome to the introduction to astronomy. In this lecture, we are going to talk about Isaac Newton and gravity and how that has then applied to orbits as we understand them. So we looked previously at Kepler. And his ideas of how things can orbit and his laws of orbital motion for the planets. And now we want to look at Newton and gravity and how we can understand where those laws come from. So let's go ahead and get started. And we want to go back a little bit first, and we want to talk about Galileo. Now, we talked about Galileo and his telescope in a previous discussion. However, we also know that Galileo gave us a couple of other things, including the concept of inertia and the idea that all objects fall at the same rate in a gravitational field. And what that means is that if you drop a hammer and a feather at the same time, that they will land at the same time. Heavier objects do not fall any faster than lighter objects. In fact, they fall at exactly the same rate. Now, we don't notice this here on Earth because we have air, and air resistance will keep the feather from falling as fast as the hammer. But if we do this experiment on the moon, we will see that they do fall at exactly the same rate. And in fact, we can look at that with what was done with the Apollo mission and we will go ahead and watch a video of that mission and listen to what was done with the Apollo 15 mission where they did this exact experiment on the moon.
Jim, we copied both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. Joe, you have a good picture there. I've got
beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
Now, what we saw there were two different things. First of all, we noticed that the objects fell at the exact same rate. The hammer and the feather hit the ground at the same time. But you may also have noticed that they fell at a much slower rate than they would here on Earth. You know how fast something like a hammer might fall when you drop it on Earth. And here we are able to see that it was much slower, showing the lower gravitational field of the moon. So let's go ahead and take a little bit of an aside here and also introduce a couple of concepts. And those are the concepts of velocity and acceleration. And what we have with those is that they're a little bit different. They're actually what we call vector quantities. A vector quantity has a magnitude, a size, and a direction. Now this means that velocity is not the same thing as speed. Speed is how fast you are going. It does not have a direction associated with it. So you could be going 50 miles per hour, for example, and that would be your speed. In order to make it a velocity, we need a direction. So 50 miles per hour, say east. And that would give it a direction, and that would be different than 50 miles per hour west. So those are different velocities, even though the speeds are the same. Now, we also look at acceleration. In acceleration, we understand in everyday language as speeding up, going faster. That is when you are accelerating. However, in reality, an acceleration occurs whenever a velocity changes. So that can be speeding up. It can also be slowing down. We often call that a deceleration, but in physics terminology, it is an acceleration. It is just not a increasing in velocity. It is a decrease in velocity. It can also occur when directions change. So if you change direction, that is also a change in velocity, because you could be going from 50 miles per hour east to 50 miles per hour north. You have changed your direction and therefore accelerated, even though your speed has remained exactly the same. So let's move on and talk about Sir Isaac Newton and a little bit about what he gave us. Sir Isaac Newton, pictured here, gave us a number of things, including the calculus as a way of solving his problems of motion and gravity. He gave us three laws of motion that we will talk about shortly, and the universal law of gravitation that we will be looking at. So a number of different things done by Newton, and those are just a few of the things that he did, but the ones we want to focus on for this class. So let's start off looking at his laws of motion, and he gave us three laws of motion. His first law, sometimes called the law of inertia, states that an object at rest, or in a state of uniform motion, will continue that motion unless acted upon by an outside force. So if an object is sitting there, it's going to stay sitting there. If an object is moving at a straight line at a constant speed, it will continue doing that. So it also means that any object not doing these things, any object that changes its motion, so any object that accelerates, must have an outside force acting upon it. So a car crash could be one example of this, pictured here. If the car is stopping, then it is changing, it is accelerating, and you'll note that the person, or in this case the crash dummy inside, is still moving forward even though the car stopped. So while the car stops, the person will accelerate forward. And you're familiar with this. If you have to slam on your brakes, you will feel yourself lunging forward. Well, that's because of the law of inertia, that you want to keep moving forward, but the car is then going to stop you. So Newton's first law, the law of inertia. We also apply this to planets. If a planet is moving in a circular orbit, it is accelerating. Remember that acceleration is a change in velocity. So they are accelerating as well, because even if they're moving at a constant speed, they are changing direction and therefore being accelerated, and a force must be exerted on them. Newton's second law of motion states in two ways. We can state it in an equation, which is F equals ma. And that means that the acceleration of a body, we can also write that a little differently. The acceleration is proportional to the net force acting on the body. So it equals force, and inversely proportional to the mass. So this is really the same equation, just rewritten to solve for acceleration here. But this is what Newton's law tells us, that there is a relationship between the force, the mass, and the acceleration. So how can we see how this works? Well, we look at the examples here of a person pushing a ball with what the force, and then pushing a car with the same force. Well, because of the force is the same. So we have identical force here on both cases. We push the ball and the car with the same amount of force. Well, the masses are different. So if you have a much smaller mass, you are going to get a larger acceleration. If you take that constant force and divide it by a very small mass, the acceleration will be larger than if you divide it by a large mass. So the ball will then accelerate, and we see A1 here much larger than A2. But the forces are identical. It is the masses that are different. So the acceleration depends on the force acting on it. If you push with more force, you will accelerate something more. But it also depends inversely on the mass. The greater the mass, the harder it is going to be to accelerate that object. All right, let's go ahead and look at the third law then. The third law, sometimes called action and reaction. For every action, there is an equal and opposite reaction. So launching a rocket is one example of this. The material is expelled downward at a very high speed, and the reaction then pushes the rocket up and launches it into space. So it is an example of Newton's third law of motion, that if you push something in one direction, they're going to have motion in the other direction as well. So it's a way of, again, looking at the rocket launch as one example of Newton's third law. Now, the other thing we wanted to look at for Newton was his law of gravitation. His universal law of gravitation states, and here it is stated in words, that the gravitational attraction between any two bodies is proportional to the product of their masses and inversely proportional to the square of their distance. Let's write that as an equation. F equals, and it's a negative, g m1 m2, that's the product of the masses, divided by the square of the distance. G is the gravitational constant that is in there. It has a specific value we really don't need to worry about for our class here. We consider it universal because it applies to any two objects in the universe with mass. So you could figure out the force of attraction between yourself and the moon. All you need is the distance between you and the moon, and the masses of the moon, the mass of yourself, and the gravitational constant, and you could calculate that force. The negative sign is because it is always an attractive force pulling things together. You will never get a repulsive force out of gravity because everything here has to be positive. We will always get a negative value here because g is positive, masses cannot be negative, and the radius squared, the distance, cannot be negative. So it is always an attractive force. Gravity never pushes things away. Now we could look at a couple of examples here, and we're going to look at a few here. What happens if with this equation if we do a few things? So these are some of the things that are reasonable to expect. You don't need to do the calculations to calculate the exact force for my class. But we can look at things like what happens if you double the mass of one or both objects? What if you triple the distance between them or bring them 4 times closer together? Let's look at those examples briefly. And what you find, first of all, what if we double the mass of one of the objects? Well, all we've done is replaced m here by 2m. So when we multiply everything out, we get just a factor of 2 in front of the force, and that this new force is twice the value. So if we double the mass of one of the objects, the force of attraction will be twice as much. What if we double the mass of both objects? Well, now we have the mass there twice. 2m and 2m, and 2 times 2 being 4, everything else is still the same. We will get the force being 4 times as much. So if we double the mass of both objects, the force would be 4 times as great. What if we look at the distance? What if we triple the distance between the objects? So what was r becomes 3r. Well, 3r squared is 9r squared. Is 9 becomes 9 and the r squared. So 3 squared is 9, r squared is still r squared. And we will get that the force will now be 1/9. So we have tripled the distance. They are further apart, and the force is going to be 1/9 as much. And this is the inverse square law. So it doesn't just drop off as the distance. So you don't double the distance and that doesn't mean half the force. It actually, if you triple the distance, it is 1/9 the force. And the same thing can happen if you increase and bring the objects closer together. In this case, we are bringing them 4 times closer together. So the distance is now 1/4 of what it was. And that is going to be 1/4 squared, which is 1/16. But that's 1/16 in the denominator, which means 16 in the numerator. So the force will now be 16 times the original force by bringing those two objects 4 times closer together. So those are just a few examples of some of the things you can do with Newton's law of gravitation without actually going through detailed calculations. Now, what does this apply for Kepler's third law? Remember, Kepler gave us p squared equals a cubed. Newton revised this in a simplified version to give us p squared times m1 plus m2 equals a cubed. So m1 is the mass of one object, m2 is the mass of the other object. What this means now is that we can determine the mass of a system by measuring its semi-major axis, the average distance between the two, and the orbital period of the. So if we determine those orbital period, we can determine the mass. We're going to find this very useful for determining masses of stars and galaxies further when we get further out into studying other parts of the universe. So let's go ahead and finish up with our summary. And what we've looked at, we looked at a couple things. We looked at the video that showed that all objects fall at the same rate regardless of mass. We briefly looked at Newton's 3 laws of motion and looked at his universal law of gravitation and some examples and how that can be applied to a modification of Kepler's 3rd law. So that concludes this lecture on Newton and gravity. We'll be back again next time for another topic in astronomy. So until then, have a great day, everyone, and I will see you in class.